Hi, and welcome to our session number 7. Session 7. We agreed that this is going to be a problem-solving session, so today I'm mostly going to be doing problem-solving. Now, some things are due noting. First of all, since we haven't done much about differentiability, we just literally defined what it means to be differentiable, and maybe mentioned a few notes and remarks, but we haven't done any real thing with differentiability. Okay, so that's why for today we're just going to be doing sort of basic stuff, very basic stuff, just to get familiar with how to do derivatives, okay? And the situation would be, at worst, some function defined from an opposite set of the reals into some known vector space, okay? But some, like half of the exercise, I think they're going to be about functions which are going from the reals and mapping into the reals, okay? Just to get a feeling of differentiability. And of course, as we go further, we're going to explore the other possibilities, okay? As we go further into differentiability. The last time I was saying there were two things I wanted to do before starting today, which is, first of all, I wanted to talk about equivalence of norms, okay, implying that differentiability is preserved, okay, in a sense which I will explain. And the second one was some more talking about the Landau notation, which I briefly discussed last time. Just gave an example of how to compute a limit using the Landau notation, which is useful, which is very useful. But I wanted to talk more about the properties of the Landau notation and how we usually use this notation in known vector spaces situations. Okay, so as for the first one, okay, I'm gonna do it as an exercise. I'm gonna do this as exercise number 0, okay, just as a warm-up. And this thing, the Landau notation, is what I'm gonna be starting with today. I'm gonna discuss this a bit, okay. So last time, if you remember, we defined this definition. So F is from some open subset U of E into F, known vector space, okay. And I was saying that okay, so let's say you have some other function G as well from U subset E to F. And let's suppose without loss of generality that U is an element, 0 is an element of U, okay. So I say that f of x equals little o of g of x if it's true that the limit as x goes to 0 of norm f of x divided by norm g of x equals 0. Okay, simple as that. Now, we might use some other weird notations as well. So we might say that f of x equals little o of g of x to the power n. Although, of course, when g lands inside a vector space, known vector space, it usually doesn't make sense to exponentiate it, okay? And certainly I don't want you to understand the exponentiation as a repeated composition, because it's not the way we are doing it here. So what this means is that, by definition, this means that the limit as x goes to 0 of norm f of x divided by norm g of x to the power n equals 0. Okay, so we're actually talking about the norm to the power n. So when we use the Landau notation this way, we're meaning with respect to norms exponentiate. Okay, there's no sense in which a vector is exponentiated inside a general known vector space. What are some cool properties about the Landau notation? So when you're in the reals, everything works smoothly. So if you have a function going from some open subset of the reals to the reals, okay, you can safely say that, say many things. So little o of x to the n plus little o of x to the m equals little o of x to the power, the minimum between n and m. Okay, this works. When you're saying little o of x to the n times little o of x to the m, this is the same as saying little o of x to the power n plus m. Okay. Same thing for division, what you expect for division, and what, of course, subtraction is no different than addition. So this is a remark, okay. If I'm saying minus little o of x, it's the same as saying little o of x, okay. These two things are equivalent. So it doesn't matter, the negative sign does not matter much in terms of when it's in front of the little o, okay. And what are the things? So there are some other properties like when you're doing Taylor expansion, okay. You can also use little o, okay, as if it is a genuine object, okay, when doing Taylor expansion, for example, okay, finite expansion to find the limit of a function. And this is all when you're talking inside the real case. Now, when we're talking inside the general case, it might not make sense to say something like little o of x to the n times little o of x to the m. Okay, right? Because let's it might make sense to say this, but like it wouldn't produce anything meaningful, right? So what does this mean actually? So I'm saying there's a function f which is equal to little o of x to the n, and some function g which is equal to little o of x to the m, When I'm multiplying these two things, okay, it's as if I'm multiplying f by g. This generally does not make sense unless you are inside the, I don't know, inside the Hilbert space or the pre-Hilbert space, an inner product space, in which multiplication has some sort of meaning. But even then, it's not that straightforward. Okay, so something like this, okay, would not make sense generally. Okay. Now, addition of little o is fine. Okay, it's fine because if I'm saying little o of x to the n plus little o of x to the m, it's as if I'm saying there's a function f of x which equals this thing and some function g of x which equals this thing, and I'm adding these two functions, which is fine, right? Which is fine. And yeah, so the thing is, if you are adding two functions which have these little o of x to the n, little o of x to the n, you're talking about the norm of f of x, right, plus g of x. Okay, and you want to check if this, when divided by the norm of x to the power, so this is the same as little o of x to the power minimum between n and m. And just so we don't use confused notation, let's just say little o of x to the m, assuming that m is less than or equal to n. Okay, so then you're checking if this thing goes to 0. Okay, but then triangle inequality, this tells me that norm f of x plus g of x, okay, this is less than or equal to norm f of x plus norm g of x, right? And then if I'm dividing by norm x to the power m, I can separate this denominator, okay, separate the numerator to get this thing. And then, of course, I know that this goes to 0 because already f of x divided by norm f of x divided by x to the n goes to 0. When you're dividing by a smaller power of x, of norm x, you're going to get 0 as well. And this thing goes to 0 as well because g of x is little of x to the n. So yes, it does work this way. It's, for addition, okay. Subtraction, said it's not something important, it's here as addition. And yeah, so just like multiplication doesn't make sense generally, also division does not make sense generally. Okay, now these are a few notes. Okay, we might be dealing with the little o notation in some other kind of ways. I'm not sure. Okay, we'll see this with time. But whenever I'm going to use some peculiar property of little o, which is not immediately obvious, I'm going to be doing the required proof to show you how it works. Okay. For now, we don't need to be worried much about what it means and how and why. In Taylor's theorem, we're going to see something like f of t0 plus h being equal to f of t0 plus h f prime of t0 plus h squared over 2 f double prime of t0, let's say, plus little o of h squared. Okay. And here little o will appear naturally, and it would be useful to refer things this way rather than saying, well, this is a certain remainder, a function of h, and the remainder divided by norm h squared will go to 0. This is more painful than just saying little o of h squared. Okay, and of course this is some version of the Taylor theorem. Okay? And generally, in vector space as well, does not make sense to multiply h by f prime, whatever these things are. Okay. Instead, you're going to see something like df of t0 applied to h, and d square f of t0 applied to h squared, etc. Okay, we're going to see these things later. Okay, for now, let's start with today's first zeroth exercise. Okay, so exercise 0. This is the thing about the norms, equivalence of norms. So let's say you have some map. Okay, actually, this thing we should have verified to prove that differentiability is well defined in the manner in which we defined, but it also, so technically speaking, it's not a requirement, okay, but morally speaking, it's a requirement. Because we're going to be using differentiability, we're going to be using norms interchangeably with differentiability, and this requires some awareness, at least, of how awareness that really is not, differentiability is not affected by changing the norms as long as the norms are equivalent. Of course, once you change the norms and the norms are not equivalent anymore, you might run into trouble. Okay, so let's state the exercise. So let's suppose that f from some u subset of e into f. Okay, these are vector spaces for now. Okay, okay, let's say non-vector spaces. Okay, but I will now explicitly say what are the norms on them. Okay, I needed to say non-vector space because this being open doesn't make sense inside the vector space generally. Okay, so let's say E is equal to some norm E1. Okay, and it's also equal to some norm E2, and F is equal to some norm F1 and some other norm F2. Okay, and suppose that norm E1 is equivalent to norm E2, and norm F1 is equivalent to norm F2. Okay, And suppose that F looked at as a map from the U, which is an open subset of the normed vector space E with the norm 1 on E, the first norm, into F with the first norm on F, okay, is differentiable. So this means, of course, that df of A exists for every A inside the, let's just say differentiable at some point A, okay. Let's just say F is differentiable at A, some A in U, okay, meaning that there is some linear map which is continuous df of A, okay, and L of EF, and this thing is unique, okay. And let's just call it the derivative with respect to these norms, okay. And let's verify that actually it is the same as differentiability with respect to the other norms that we said are equivalent, okay. So what do we want to prove actually? We want to prove that, very simply, okay, we want to prove that the limit as h goes to 0, okay, with respect to okay, this is what we have. Let me state what we're gonna be proving. Okay, so this is a given. It's given, okay, and required to prove. So required to prove that F as a map from U, which is open inside E with the second norm, into F with its second norm, okay, is also differentiable. Okay, is also differentiable at A, and its derivative is the same as the derivative with respect to the first two norms. Okay, so yeah, so I want to say further things. So it makes sense to say, okay, U is open again inside this thing in the same sense in which you are saying it's open here, because when we have equivalent norms, we're assuming that these two guys, norm E2, norm E1, are equivalent. So open sets for the first are the same as open sets for the second, and vice versa. Okay, so there's no confusion here that arises. Okay, so what we want to prove, so in actually we want to prove that the limit as h goes to 0, okay, of the norm of f of a plus h minus f of a minus df of a h with respect to norm f2 divided by the norm of h in E2, this thing equals 0. And we have proven this way simultaneously that f is differentiable and the derivative is this df of a, which is the same as the derivative with respect to first norms. Okay, so this is rather straightforward. Okay, first of all, I know that norm f2 is equivalent to norm f1. Okay, and this implies that there exists some a positive, okay, such that for all y in f, okay, it's true that the norm of y in f2 is less than or equal to a times the norm of y in f1. And second of all, I know that norm E2 is equivalent to norm E1, but because, okay, so let me just give you a heads up. I'm gonna be trying to prove that in the numerator, okay, numerator is less than some certain quantity and denominator is bigger than some certain quantity, okay, and then the fraction is gonna be less than some certain quantity, which I want to prove going to 0, okay. And this quantity will obviously be just about the differentiability with respect to the first norms. So that's why I want the numerator to be less than something. Okay, that's why I'm using this side of the equivalence of these norms. And for the denominator, I want the norm E2 to be bigger than some thing. So there exists some B positive, okay, such that for all x in E, it's true that the norm of x in E2 is bigger than or equal to B times the norm of x in E1. And that's what allows me to say that this fraction, norm f of a plus h minus f of a minus df of a h in f2 divided by the norm of h in E2, okay, this thing is less than or equal to the first bound a times, okay, so a times the norm of f of a plus h minus f of a minus df of a h in f1 divided by b times the norm of h in E1, right? So which is of course a over b times this fraction, f of a plus h minus f of a minus df of a h f1 over h in E1. And I know that this quantity goes to 0 by the very definition of the derivative, right? This is the same thing we wrote at the beginning. Anyway, so this is what we were given. Okay, we didn't write it explicitly, but this is exactly what it means for f to be differentiable with respect to these two norms and its derivative to be df of a. So this thing goes to 0, and this thing is a constant, so the entire thing goes to 0. If you are already non-negative, okay, and you're less than something that's going to 0, then you yourself are going to 0. Okay, so the limit, so this implies that the limit as h goes to 0 of the norm of f of a plus h minus f of a minus df of a h in f2 divided by the norm of h in e2 is equal to 0. And therefore we get what we want. Okay, so equivalence of norms preserves differentiability and preserves the function, which is the derivative of the original function. Yes, it preserves the derivative itself. And now we're in place to start with our exercise sheet. Of course, if you want this sheet, you can just request it. Okay, it's I already have it. Okay, I'm going to be following the enumeration, the numbering which is followed in this worksheet. So I'm going to refer to exercise 10 as exercise 10. Okay, yeah. So let's start with exercise 1. So exercise 1, what it says is that E and F are two non-vector spaces. Okay, whenever we are talking about different non-vector spaces, we're going to be using the same notation for the norm. Where in context, it's be understood that the norm on this guy is norm E and the norm on this guy is norm F, and they might possibly be different. Okay, but I'm going to be using the same notation for norm just because it does not matter mostly so long as you understand what you are working with. Okay, it does not matter to mention explicitly norm. Okay, unless serious confusion can arise. So yeah, the F are two non-vector spaces. Okay, and the F is a map from some open subset, some open interval AB in R into E. Okay, given that F is differentiable on all of, we just need it to be differentiable at T0. Okay, so the statement goes like this. Okay, so F is differentiable at some T0 side AB. Okay, and consider. Okay, so this is the first given, and let T be a mapping inside L of EF. So T is a linear continuous map, okay, or linear bounded map in the sense of the linear maps. So here given, so let G from AB into F be the map given by G of T equals T of F of T. Okay, so in other words, G is equal to T round F. Okay. Now, we're asked, so of course, F is going from AB into E, and T is going from E to F, so their composition naturally goes from AB to F. Okay. We are required to show that, so show that G is differentiable at T0, the point of differentiability of F, and G prime of T0 is equal to T of F prime of T0. So let's do that. Okay, so let's first of all remember what we talked about: maps going from an open subset of the reals into a non-vector space. Okay, let's call it G now. Okay, just to make sure we're not confusing with whatever we have in this exercise. So we said, okay, if you have some H going this manner, okay, although derivative of H at a point A will be a map between a linear map from R to G, we know that this thing is isometrically isomorphic to G. It can be identified with G. So that's why the derivative of such a map, which has a domain inside the reals, okay, the Euclidean real line, we're gonna just say H prime of A, and we're gonna think of it as an element of G, because it's really an element of G. Okay, the DH of A is gonna be a linear map from R to G, so it's gonna be identified with the H of with DH of A of 1. Okay. Because remember, this theorem talked about that a linear map from R to a non-vector space is determined by its value at the point x equal 1. Okay, so that's why it's the same as an element of G. Okay, so that's how we are going to be thinking about this kind of differentiability. And to study the differentiability of such a map, I'm going to do it in the same manner I'm going to do here. Okay, so I'm going to look at the limit as h goes to 0 of G of T0 plus H minus G of T0 divided by H. Okay, and this makes sense because this thing is a vector and this thing is a scalar. Okay, and of course, ideally I would write okay, this thing 1 over H times G of T0 plus H minus G of T0 to indicate that I'm multiplying a scalar by a vector. But let's move on past this and just use this notation for convenience. Okay, doesn't matter. Okay, so what's this? This is the limit as H goes to 0 of what? G of T0 plus H is by definition T of F of T0 plus H, right? And minus T of F of T0. this is g of t0, divided by h. Okay, now since t is a linear map, okay, we're gonna get the same as limit as h goes 0 of t of f of t0 plus h minus f of t0. Okay, this thing all inside t, because t is linear, okay, divided by h. And again, since t is linear, you can get the h inside, so this is just the limit as h goes 0 of t of 1 over h times f of t0 plus h minus f of t0, okay? And since t is continuous, okay, we assume that t is continuous, t belongs to L of EF, remember this was the given, okay? So this is the same as t of the limit as h goes to 0 of 1 over h, f of t0 plus h minus f of t0, okay? And by the very definition of derivative, this thing is just t of f prime of t0, okay? So we're done. So g is differentiable at t0, okay? And this derivative is just this thing, okay? T of f prime of t0. So we're done with exercise 1. This was just a warm-up, okay? Let's move on to what's exercise 4 here, okay? So exercise 4, it's statement, okay? So let E be a non-vector space, okay? And recall that we defined L of E to be L of E, okay? So it's just the linear continuous maps from E to itself, okay? And let F, okay, from R to L of E, so F is defined on all of R, okay? And assume that, okay, such that, first of all, F is differentiable at 0, okay? Second of all, f of t1 plus t2 equals f of t1 round f of t2, composition of functions, okay? So remember, f is going from R to L of E. So what's happening is that when you have a real number t, okay, f of t itself is a map from E to E, okay? So it looks something like this. F of t associates to each x in E some f of t of x, okay? Let's be sure that we understand this well, okay? Moving on. So, of course, it makes sense to talk about composition of such two entities because f of t1 and f of t2 are both themselves maps from E to E. They are linear maps from E to E, okay? Continuous as well, by assumption, okay? So let me just delete this thing, okay? And the third assumption of ours, okay? So the third condition is that f of 0 equals 1, or if you want the identity, the one of E, okay, or if you want the identity of E, whichever way you want to call it, okay? Just going to use the notation f of 0 equals 1, okay? Okay, so this is the given. Now we are asked to show that, so show that f is differentiable on R, so at every point in R, and that f prime is also continuous on R, okay? So in other words, okay, this whole thing is the same as saying, okay, suppose that, or show that f is of class C1 on R, okay? And of course, naturally, the first thing we're going to do is going to prove f is differentiable and find f prime, and then prove that f prime is continuous, okay? So how do we do this? We start with the definition of the differentiability, okay? Of course, f is again a map from R to L of E. So we're going into a known vector space, but our domain is the real numbers, okay? So again, you can use this thing. So limit as h goes to 0, okay, of f of t0 plus h minus f of t0 divided by h, okay? And let's look at this thing. Let's look at f of t0 plus h minus f of t0 divided by h, okay? By the second property of h, of AF, okay, which is that f separates addition into composition, okay, this thing is the same as f of t0 round f of h minus f of t0, okay, divided by h. Now, of course, since the composition map is linear, right, this is something we talked about last time. We talked about how it's bilinear, okay, bilinear, that's what I wanted to say. Bilinear and continuous, actually, okay. So we can factorize, so to speak. So this is the same as f of t0 minus or f of t0 composed with f of h minus 1, right? Bilinearity implies linearity in the second argument, okay? And this is the f of t0 itself is just f of t0 composed with the identity map, okay? So I literally have f of t0 round f of h minus f of t0 round 1. And this is why it makes sense to take f of t0 as a common, so to speak, okay? Divided by h, okay? And since again, since again composition is bilinear, you can insert the scalar h inside. So this is the same as f of t0 composed with f of h minus 1 divided by h. Okay. Now let's look at this curious thing here. Okay. This is the entire world, because f of t0 is just a constant, right? So f of h minus 1 divided by h. What's this thing? Okay. 1 is by the third assumption. 1 by the third assumption. This is f of 0, right? So this is just f of h minus f of 0 divided by h. Okay. Or if you want to make it more clear, this is f of 0 plus h minus f of 0 divided by h. Okay, but what do we know? Our first assumption was that f is differentiable at 0, right? So this thing here, okay, its limit is what? It's just, so to write the limit of this thing, limit of f of h minus 1 over h as h goes to 0, which is the limit of this guy, okay? This is just f prime of 0, okay? Now let's look back at our case here. So what I have is f of t0 plus h minus f of t0 divided by h, right? And I'm computing the limit as equals to 0 of this thing, okay? I figured this is the same as the limit as equals to 0 of f of t0 composed with f of h minus 1 over h, okay? But since the composition function is continuous, okay, I can insert the limit inside. So I'm going to get the f of t0, okay, f of t0 composed with the limit as h goes to 0 of f of h minus 1 over h, right? And yeah, so this is f of t0 composed with f prime of 0, okay, just as we remarked here, right? So I'm done, okay? I've proved that f is differentiable at t0. t0 was arbitrary, okay? And so let's just say t, okay, differentiable at t, and f prime of t is equal to f of t composed with f prime of 0. Okay, this is the derivative. Okay, now I want to prove that f prime is continuous. Okay, and how do I do that? I just look at f prime of t0 plus h minus f prime of t0, and I prove that this thing has limit 0 as h goes to 0. Okay, what's this thing? This is just f of t plus h round f prime of 0 minus f of t round, say t0, okay, t0 minus f of t0 round f prime of 0. Okay, once again, this is just f of t0 plus h minus f of t0, all composed with f prime of 0. And now when I want to take limits, limit as equals to 0, f prime of t0 plus h minus f prime of t0, this thing we started with. Okay, this is the same as the limit of this guy. Okay, so f of t0 plus h minus f of t0, all composed with f prime of 0. Okay, we talk about the limit of all of this thing. Again, since the composition map is continuous, I can insert the limit inside, so it's just the limit as h goes to 0 of f of t0 plus h minus f of t0. Okay, this thing composed with f prime of 0. Okay, and this thing is 0 since f is continuous at t0, right? So this is just 0, the 0 map composed with f prime of 0. Okay, and this is just 0 because the 0 map composed with anything is 0. Okay, so I've proven what we want. We've proven that f prime is actually continuous, and therefore f is of class C1 on R. Okay, so we're done with this exercise. Next on our list is what's here mentioned as exercise 5. Okay, so exercise 5, and this exercise is actually a theorem. It's called Darboux theorem, okay, after the mathematician Darboux. Okay, what does this theorem say? More intuitively, it just said that the derivative of a function satisfies the intermediate value property. Okay, so the question goes like this. So let f be a map from an open interval AB in R into mapping into R. Okay, and suppose f is differentiable, okay, on all of AB. Okay, suppose there exists some alpha and beta, okay, in AB, the interval AB, okay, such that f prime of alpha is strictly less than f prime of beta. Okay, try to show that. So show for all mu belonging to the open interval f prime of alpha, f prime of beta, okay, there exists some C inside the open interval alpha beta, okay, such that so assuming that this is generality that alpha is less than beta, okay. Of course, if beta is less than alpha, then it's inside the interval beta alpha, doesn't matter much, okay. Such that mu equals f prime of C. So literally saying, okay, this is the graph, intuitively speaking, this is the graph of f prime somehow. Okay, there's a point, so there's a point alpha, there's a point beta, this is the open interval AB, say, okay. And there's at f prime of alpha, okay, is, so we want it to be negative, right? F prime of alpha, oh, we just want it to be less than f prime of beta, okay. So f prime of alpha, and this is some f prime of beta, okay. It's corresponding to beta, okay. So we're saying that if you take something inside the range between f of alpha and f of beta, okay, some mu on the way, okay, some mu over here, okay. We're saying that for this mu there must exist some C between alpha and beta such that, well, f prime of C is equal to mu. So we're literally saying that derivative f prime should satisfy the intermediate value property. Now what's curious is that f prime does not need to be continuous, okay? Does not need to be continuous anywhere. But it will satisfy the intermediate value property. Okay, so that's really a strong theorem. Okay, now the first thing we're going to be doing, so spoiler, I'm going to start solving the exercise now. If you don't want to see the solution immediately, just pause the video, okay? And what I'm going to be doing is I'm going to start with some function which will make my life easier, okay? So let's take g of t to be this function given by f of t minus mu t, okay? So mu is given, right? Just say let mu be inside the interval that we want to work with, okay? So let mu belong to the interval f prime alpha f prime beta, okay? And consider g of t to be this thing. So g prime of t is just f prime of t minus mu, right? And to say that there exists some c in alpha beta such that f prime of c equals mu is the same as saying that g prime of c is equal to 0, right? So we want to find a point c such that the g prime of c is equal to 0. Furthermore, g prime of beta, or let's start with alpha, okay? So g prime of alpha, which is f prime of alpha minus mu, okay, is going to be strictly negative because mu is inside the interval f prime of alpha, f prime of beta, right? So g prime of alpha is going to be negative, and g prime of beta, which is f prime of beta minus mu, is going to also be strictly positive. Okay, so these are our assumptions. Let's make them clear. So again, the problem is reduced to the following. Okay, so g from AB inside R into R. Okay, we know that for alpha less than beta, okay, alpha and beta belonging to the interval AB. I know that g prime of alpha, so g is differentiable, okay, differentiable. I know that g prime of alpha is strictly negative, g prime of beta is strictly positive, and it's required to prove that there exists some c inside alpha beta such that g prime of c is equal to 0. Okay, so this is our target. So what we're going to be doing here is going to be invoking an idea which comes from the extreme value theorem, okay? So remember from basic calculus or from high school that if you have a function, okay, a real function, which admits a local maximum or a local minimum, okay, the derivative, if it's differentiable, the derivative at this local maximum or local minimum is going to be 0. Okay, so if I successfully prove that g has a local minimum or a local maximum inside the interval alpha beta, then I'm game because then g prime of c will necessarily be equal to 0. Now, why is this the case? So let me just put this as a remark, okay? So remark, if c belonging to some interval alpha beta is a local extremum, okay, say minimum without loss of generality, okay, of g differentiable over alpha beta, okay, differentiable, then g prime of c will necessarily be equal to 0. Okay, so why is this the case? So since g is a local minimum, there exists a neighborhood of c over which g of c is a minimum, okay, it's less than or equal to g of x for all x inside this neighborhood. Okay, And then when I'm considering the limit as h goes to 0 of g of c plus h minus g of c divided by h, I can do two tricks. Okay, first trick is that I'm going to go from 0 plus. So I'm going to be going to the right of c. The perturbation is happening to the right of c. Okay, so since we can choose h is small enough. Okay, h is going to 0, so we can choose it arbitrarily small. So I'm going to choose h in such a way that c plus h will lie inside the neighborhood, which I'm talking about, in which c is a minimum. Okay, so then necessarily this numerator is going to be non-negative. Okay, because g is a minimum here. Okay, and the h itself is non-negative as well. So this thing is going to be non-negative. Okay, that's the first step. Second step is going to consider limit from the left. Okay, h goes to 0 minus of g of c plus h minus g of c divided by h. Now again, since c plus h can be chosen to be lying inside the interval, inside the neighborhood we're talking about, this thing is again a non-negative quantity. Okay, but this time h is non-positive because h is going to 0 minus. So that's why this thing will turn out to be less than or equal to 0. So I've gotten two things. So of course both of these are equal to g prime of c. Okay, why? Because g prime of c is the limit as h goes to 0 of this quantity, which is the same as 0 plus or 0 minus. Okay, so I conclude that g prime of c is greater or equal to 0 and g prime of c is also less than or equal to 0. The only way this can happen is if g prime of c is equal to 0. Okay, so this is the only thing we needed to remark before we now start with the proof. Okay, so what we're going to be doing is we're going to say, okay, so g, since it's defined in the interval AB, entire interval AB, and alpha beta, the segment, okay, lies entirely inside AB, okay, g is necessarily continuous on the interval alpha beta, closed interval alpha beta, which is a compact interval. Okay, so this is compact. And by the extreme value theorem, this means that g does actually admit a minimum on alpha beta. Let's call this minimum c. Okay, this does not mean that there is no other minimum, but let's call whatever minimum. So there exists some point. Okay, so there exists some c inside alpha beta, the closed alpha beta, such that g of c, okay, equals the minimum of g of x with x belonging to alpha beta. Okay, and okay, so if c actually, so if c lies inside the open alpha beta, okay, then by what we did above, it follows that g prime of c is equal to 0, and we are done. Okay, now let's try to prove that c cannot be alpha and that c cannot be beta. Let's do that. Okay, so if we do that, then we are done. So suppose c equals alpha. Okay, so this means that alpha is a minimum of g on, so g of alpha equals the minimum of g of x over the entire interval alpha beta, closed interval. Okay, let's look at, so of course g is differentiable at alpha, and remember that we are already, so we are born inside the interval alpha beta. Okay, and then we are restricting ourselves to the closed interval alpha beta, which is inside the open interval AB. Okay, so actually the function g is differentiable at alpha, not just to the right. Okay, just differentiable at alpha. Okay, so in any case, I can just look at the g prime of alpha, okay, which is the limit as h goes to 0 of g of alpha plus h minus g of alpha divided by h. But I want to make use of the fact that alpha is the minimum over the interval alpha beta. So that's why what I'm going to be doing is I'm going to be approaching from the right. Okay, so h goes to 0 plus. Okay, when h goes to 0 plus, I'm to the right. Okay, so alpha plus h, since h is small enough, this will lie inside the interval alpha beta. Okay, and then this thing will be non-negative because alpha is a minimum. Okay, and h of course is non-negative because it's going to 0 plus. So that's why g prime of alpha, the result of this limit, is going to be non-negative. Okay, but what do we know? We know that. So where is it? Okay, g. So I just want to show you this thing. Okay, g prime of alpha is strictly negative. Okay, and remember that g prime of beta is strictly positive because we're just going to need this in a few steps. Okay, so g prime of alpha is strictly negative, but here I got that g prime of alpha is greater or equal to 0. So this is a contradiction. Okay, so thus it cannot be that c equals alpha. Okay, so c does not equal to alpha. Okay, now if c equals beta, we are using a very similar argument. Okay, so let's look at g prime of c. Okay, or g prime of beta if you want. Okay, so g prime of beta equals the limit as h goes to 0 of g of beta plus h minus g of beta divided by h, right? And since I want to make use of the fact that beta is the minimum over the is the point at which the minimum is attained on the interval alpha beta, I want h to go to 0 minus. Okay, so I'm going from the left. And so this thing will be non-negative, of course, because beta is a point of minimum, and the h is going to be less than or equal to 0, okay, because h is going to 0 minus. So I conclude that g prime of beta, which is the result of this limit, is going to be less than or equal to 0. Okay, but I know that g prime of beta is strictly positive. Okay, this is a contradiction. So therefore, also we cannot have that c equals beta. So c does not equal to beta. So therefore, it must be that c lies inside the interval alpha beta, the open interval beta, and therefore the result follows. Okay. So that's for this exercise. Okay, let's move on now to exercise number 6 on the sheet. Okay. Exercise 6. So what is this exercise about? So you have a function f from R to R. Okay. Recall that for such a function for any function really, okay, whose domain is the same as the codomain. We say that A is a fixed point of f if it's true that f of A equals A. Okay, if f fixes A. Part 1, okay, says suppose that f is differentiable on R, okay, on all of R, and f prime of t is never equal to 1, okay, for all t in R, okay. Show that f has at most one fixed point. So this means that f does not necessarily have a fixed point, okay. But if it has a fixed point, then this fixed point is unique. There's no more than one fixed point, okay. So how do you prove this? Okay, how do you prove this? First thing that comes to my mind is a proof by contradiction. Okay, these kind of things really suggest this because it's showing that there's no more than one fixed point. Okay, let's suppose that. So suppose there exists two fixed points. Okay, let's see what we get. Suppose there exists some a and b in R. Okay, such that, let's say, without loss of generality, a is strictly less than b, okay, such that f of a equals a and f of b equals b. Okay, how do we transform these information into some very similar information? The usual trick is to take this function g of t to be f of t minus t. Okay, the advantage is that you can say g of a, okay, equals f of a minus a. Okay, this is 0 because f of a is equal to a, and g of b is also 0. Okay, so f of b minus b, which is also 0. And the advantage is that now I have a function which has equal values at two different points. And this should remind you immediately of the Rolle's theorem, okay, the very classical Rolle's theorem. And what does the Rolle's theorem say? Okay. First, of course, G is differentiable on all of R because F is differentiable on R. So I know that G is differentiable, in particular, on the interval AB. Okay, and moreover, G is continuous on the closed interval AB. Why? Because it's continuous everywhere. Because it's differentiable. Differentiability implies continuity. Okay. So y is and I have that g of a equals g of b, right? Because both of them are 0. Okay. I wanted to say something. I'm not sure if I've proven before that. Maybe in the last session that differentiability implies continuity. Okay. I will check this later, and if I haven't done that, I will do it next time. Okay. So just keep in mind that differentiability implies continuity always, okay, in whichever situation you are. So and this is something that you should know from basic calculus, but we will do for the general case of normal vector spaces. So I have these three conditions, which are the classical conditions for the Rolle's theorem, and I conclude that there exists some point C inside the interval AB, okay, such that G prime of C is equal to 0. Okay, and what's G prime? Okay, so G of t is equal to f of t minus t, right? So G prime of t is just f prime of t minus 1. And saying that G prime of C equals 0, this is saying that f prime of C equals 1. But I know by assumption that f prime of t is never equal to 1. Okay, so this is a contradiction. And therefore my assumption must have been wrong, and therefore there are no two distinct fixed points. So there's at most one fixed point. Okay. Part 2 of this exercise, okay, it's just about calculation. So given the function f of t equal t plus 1 over 1 plus exponential t, okay, and you're asked to show that first, f has no fixed point, okay, on R, and second, that for all t, f prime of t is between 0 and 1, okay. Now, the moral of this part 2, I'm gonna explain after we do part 3, okay. So, to do this exercise is really straightforward. Part A, f has no fixed point, so suppose there exists some a in R such that f of a is equal to a. Okay, what does this mean? I know what's f, so let's just write down f of a. So a plus 1 over 1 plus exponential a equals a. Okay, and this implies that 1 over 1 plus exponential a equals 0, and this is obviously a contradiction, right? So f cannot have a fixed point. So that's for part A. For part B now, just calculate f prime. Okay, so f of t again is t plus 1 over 1 plus e exponential t. So f prime of t equals 1 minus et over 1 plus et squared, right? So then this thing is obviously strictly less than 1 because this thing here is strictly positive. I'm subtracting something strictly positive from 1, so I'm going to get something that's strictly less than 1. Okay, now why is f prime of t strictly bigger than 0? Well, because this thing again is strictly less than 1. Why? Because 1 plus et squared, okay, is clearly bigger than et strictly. If you want to see it, you can just expand, right? Et squared is equal to 1 plus e2t plus 2et. Okay, and well, at least I know that 2et is bigger than or equal to et, so this is bigger than or equal to 1 plus, and this is greater or equal to 0, this is bigger than or equal to 1 plus et, which is strictly bigger than et, if you want a very simple proof, okay? And so, the fraction et divided by 1 plus et squared, this thing is strictly less than 1. So 1 minus this thing, which is f prime of t, is going to be strictly positive, okay? So, conclude that f prime of t is squeezed between 0 and 1, okay, for every t in R. You are done for this part 2. So part 3, now part 3 asks you to prove something which I think we're going to be seeing later as well, more generally inside Banach spaces. I already gave a hint before start the exercise. Not sure it is too healthy. Okay, so so suppose that f is differentiable on R, okay, and suppose there exists some a, okay, which is strictly positive and strictly less than 1, such that absolute f prime of t is less than or equal to a for every t in R. Okay, this is the given. Show that f has a unique fixed point. So there are two things to show. There is a fixed point, okay, and this fixed point is unique. Now, why is it unique? So before we even prove that it exists, we can show that if it exists, then it's unique. And how do we do this? We use part A. We use part 1. Okay. So I can say, okay, if f is to have more than one fixed point, then by part 1 there must exist some c in R such that f prime of c is equal to 1. Or if you want, so long as f prime of t does not equal to 1, okay, for every t in R, I know that f cannot have more than one fixed point if it has any. But, well, I know that absolute f prime of t is less than or equal to a. It's 2 for every t in R. And a itself is strictly less than 1. Okay. If f prime of c was to be equal to 1 for some c, then I would have that absolute f prime, I would have anyway that absolute f prime of c is less than or equal to a. Okay, so I get that 1 is less than or equal to a. This is a contradiction because a is strictly less than 1. Okay, so cannot have more than one fixed point. Now let's prove that it actually has a fixed point. Okay, so the way we're going to be doing this is to imitate the proof of the Banach fixed point theorem. Okay, for functions, general Banach spaces. Okay, it's really the same idea. Here, of course, looking at the amount of the derivative, okay, first thing that comes to mind is to use the mean value theorem, right? I mean, if I have a condition on the derivative and that's the only information I have, okay, some inequality regarding the derivative, this reminds me of this kind of thing having to do with the mean value theorem, because the mean value theorem states something like this, okay? So for x and y given in R, okay, let's say x less than y without loss of generality, okay? I know that by the mean value theorem, okay, there exists some psi inside xy such that f of y minus f of x over y minus x is equal to this f prime of psi. Okay. Now, if I take absolute value both sides, I will get that the absolute of this is equal to absolute of that, and this is less than or equal to a because f prime is always bounded by a. Okay, and I get myself this inequality: f of y minus f of x is less than or equal to a times y minus x. Now, I do not really have a very ready reason for why things are done this way, unless you know what's a Lipchitz function. Okay, so this thing here is known as the Lipchitz condition, and a would be the Lipchitz constant. So you say this function is a Lipchitz. Okay, and if you're familiar with Lipchitz functions, you know that you have many things that you can get from such an inequality, in particular the fixed point thing. Okay, yeah, so for this situation here, what's usually done is that you take a sequence which you define recursively. Okay, some sequence, you just say let u0 be 1 or anything really, and say let's recursively define un as un plus 1 equals f of un. Okay, and then you would want to have that un is convergent. If un is convergent, then you can take limit both sides here, and you just get f of the limit is equal to the limit of un, which would be the same both sides. So you get f of a equals a. Say a is the limit of un. Okay, so we are after proving that the sequence is convergent. Okay, and the way we'll do this is try to prove that this sequence is Cauchy. Okay, because we are already inside R, we don't really need to prove that it's convergent by finding its limit. We just need to prove that it converges, and for that it's enough to prove that it's Cauchy because we're inside in the Banach space. R is a Banach space. Okay, so let's try to prove that this is a Cauchy sequence. Okay, naturally I would want to look at the difference un plus p minus un. Okay, I want to prove that this thing goes to 0 as n and p go to infinity, right? So let's look first at the difference between successive terms. Okay, so if we look at un plus 1 minus un, what's this? Okay, this is f of un minus f of un minus 1, right? And this thing, okay, is by the thing we just proved above. Okay, this thing holds for all x and y, of course, in R. This thing is less than or equal to a times absolute un minus 1. Okay. And you can do the same thing for un and un minus 1. So absolute un minus 1, this is just absolute f of un minus 1 minus f of un minus 2, right? And this is less than or equal to a times absolute un minus 1 minus un minus 2 for the same reasons. And of course, what you conclude is that absolute un plus 1, so therefore absolute un plus 1 minus un is less than or equal to a squared times absolute un minus 1 minus un minus 2. And you can do this iteratively, okay, as many times as you wish. Let's say k times, and what you're going to get is that absolute un plus 1 minus un is less than or equal to a to the k times absolute un minus k plus 1 minus un minus k. Okay, you can check this thing by induction or by any other means. Okay, so this is true for every k with sufficient assumptions on k, just so we don't get a negative index or something. Now, okay, if I'm going to look at un plus p minus un, okay, let me do this as a telescoping sum. This is a very useful trick. So this is a sum from k equal 1 to p of, let's see, so I want successive terms to lead me eventually to un plus p and un. So this is going to be the starting thing. Okay, so the starting index is going to be n, and the ending index is going to be n plus p on the left. Okay, so I'm going to be wishing to have something like this. It's going to depend on n, of course, so un plus something or minus something. And actually, okay, the last thing is going to be n plus p, and this is ending in p, so this is n plus k, and then this is just before it by 1, so this is n plus k minus 1. You can verify if k is equal to 1, then this thing is just n, which is what I recover here. Okay, so this thing, by repeated use of triangle equality, is less than or equal to the sum from k equal 1 to p of absolute un plus k minus un plus k minus 1. Minus 1 is in the index. Okay. And now I look back at this golden formula here, okay? And just to not confuse the n here with the n here, let me call this m, maybe. Okay, let me rewrite this formula as this. Um plus 1 minus um is less than or equal to a to the power k times absolute un minus k plus 1 minus minus k. And in fact, okay, let me just do this, let me just keep doing this thing until I reach a point where I have u1 minus u0, okay? So I would want m to be equal to k, right? So if you keep doing this, you get plus 1 minus is less than or equal to a to the power something. We'll see what this thing is. Okay, of course, we know that k is m, so it's going to be m. Okay, and this is absolute u1 minus u0, right? So this is the ultimate formula that I have, okay? And now if I want to set, so I'm looking here at un plus k minus un plus k minus 1. So I'm going to be looking at m equal, so I'm going to be looking at m being equal to this thing here, n plus k minus 1. Okay, so setting m to be n plus k minus 1, I'm going to get that absolute un plus k minus un plus k minus 1 is less than or equal to a to the power n plus k minus 1 times absolute u1 minus u0, right? And now, so now if I go back to the sum I had here, so absolute un plus p minus un, this thing is going to be less than or equal to, here I already know that this thing is going to be less than or equal to a to the power n plus k minus 1 times absolute u1 minus u0, so I might as well put it here. The sum from k equal 1 to p of a to the n plus k minus 1 times absolute u1 minus u0. Okay, now let's take everything that doesn't have to do with k outside, so this is just a to the power n minus 1 times absolute u1 minus u0 times the sum from k equal 1 to p of a to the power k minus 1, okay? Let me do this to the power n and just keep the n minus k minus 1 inside. So this is obviously less than or equal to a to the n times absolute u1 minus u0 times the sum from k equal 1 to infinity of a to the power k minus 1. Or if you want, just take p to infinity both sides. We don't need that though. Okay, and this is a geometric series, right? Starting with k equal, if you want, 0, because this is starting with 1 and this k minus 1. And this sums to what? u1 minus u0 times 1 over 1 minus a, right? And this whole thing here, this is a constant, some constant m. And as n goes to infinity, a to the n goes to 0 because a is squeezed between 0 and 1, okay? So then the right-hand side has limit 0, and that's obviously meaning that the left-hand side, the limit as n and p go to infinity of absolute un plus p minus un is equal to 0, okay? And therefore un is a Cauchy sequence, okay? It's a Cauchy sequence. And therefore un is convergent. Why? Because R is Banach, okay? Every Cauchy sequence is convergent. So let's call the limit of un, let's call it a, okay? And let's recall that un plus 1 equals f of un. This is true for all n, right? So take n to infinity, get that a equals the limit of f of un, which is f of the limit of un. Well, because f is differentiable, so it's obviously continuous. This is f of a. So therefore, f of a is equal to a. Okay, so f has a fixed point. This fixed point is unique, as you just shown in the beginning, right? So we're done with this exercise. Now let's do the last exercise for today, exercise number 8 on the sheet. Okay, so exercise 8, it's a rather cute exercise. Let H be a pre-Hilbert space or an inner product space. So inner product space, not assuming that it's a Hilbert space, okay? And f from the open interval AB inside R into R, assuming that it's a continuous function, so sorry, from the closed interval AB, okay? Closed AB to R. So f is continuous on the closed AB and differentiable on the open AB, okay? This suggests mean value theorem right off the bat, right? Sorry, f is going into H, okay? Into H. So this kind of suggests the mean value theorem, okay? Now, it asks us to prove that, show that there exists xi inside the open AB such that the norm of f of b minus f of a is less than or equal to b minus a times the norm of f prime of xi, of course. The norm here is the norm induced by the inner product, okay? So it's so the norm of x is given by the square root of x dot x, okay? And with this property that this inner product, okay, it's a bilinear. Of course, it's bilinear always, but for now it's continuous as well. because the norm we are using is the norm induced by the inner product. Okay, and you can show this if you don't already know this fact. You can show that it's continuous with respect to the norm induced by it. So we are asked to show this thing. Okay, so let's so there's a hint, of course. There's a hint given here. So the hint is let z be equal to f of b minus f of a, and consider the map phi of t given by the inner product between. So phi of t equals the inner product between z and f of t. Okay. This phi, okay, this phi is a map which is defined on the closed interval AB, okay, inside R, and it's mapping into R because it's doing an inner product, okay, and after this inner product you're gonna become a scalar. Okay, so you can apply the mean value theorem to phi. Okay, that's as far as I can see. Okay, this is the only thing we can do to hope to get something of this sort. So let's do the MVT on phi. So we know that phi is continuous on the closed. Okay, now the continuity of phi comes from the continuity of f and the continuity of the inner product. Okay, and let me just point to why differentiability is also the case for phi. So let's say you are talking about some t0 inside the open AB. Okay, and let's look at phi of t0 plus h minus phi of t0 divided by h. Okay, this thing is just 1 over h times z with f of t0 plus h minus z with f of t0, right? And this thing is 1 over h times the inner product between z and f of t0 plus h minus f of t0. Why? Because the inner product is bilinear. And because it's bilinear as well, you can take this thing, you can take the 1 over h inside. So this is z dot 1 over h f of t0 plus h minus f of t0. And now, because the inner product is continuous, okay, when I want to talk about the limit of this thing as h goes to 0, limit, and let's say limit here as well, okay, limit. This is the same as the z dot the limit as h goes to 0 of 1 over h times f of t0 plus h minus f of t0, okay. And this thing is just z dot f prime of t0. So therefore, phi is differentiable on AB, and phi prime of t is given by z dot f prime of t. Okay, it's true for every t inside AB. So by the mean value theorem, okay, so MVT implies that there exists some psi between A and B such that phi of B, okay, so phi of B minus phi of A divided by B minus A is equals phi prime of psi, right? So in other words, phi of B minus phi of A equals B minus A times phi prime of psi. Or if you want, phi of B minus phi of A is equal to B minus A times Z dot F prime of psi. But just prove this above, okay? Now, phi of B minus phi of A, what's that thing? This is just Z dot F of B minus F of A, right? Because it's Z dot F of B minus Z dot F of A, which is this thing because the inner product is bilinear. This thing equals B minus A times the inner product of Z with F prime of psi. Okay. Now, well, Z is itself F of B minus F of A, so we are talking about Z dot Z, right? Being equal to B minus A times Z dot F prime of psi. So norm Z squared equals B minus A times Z dot F prime of psi. Okay. Now, by Cauchy-Schwarz, okay, so this is a reminder, so recall, Cauchy-Schwarz says that if you are in an inner product space, then what you have is that the inner product of U and V in absolute value is less than or equal to the norm of U times the norm of V, where the norms are the norms given by the inner product, okay? So you're going to get that the norm of Z squared is less than or equal to B minus A, because B minus A is positive, okay, times the norm of Z times the norm of F prime of psi. So if you cancel the norm of Z from both sides, then you're going to get that the norm of Z, okay, is less than or equal to B minus A times the norm of F prime of psi. Okay. Now, of course, if norm Z is already equal to 0, there's nothing to prove, right? If norm Z is equal to 0, we're saying norm F of B minus F of A is equal to 0, and that's already less than or equal to whatever positive or non-negative quantity you want. So considering that z is not equal to 0, and therefore that's why I divided by norm z both sides. Okay, and what does this thing, last thing that we got, tell us? Well, this norm f of b minus f of a is less than or equal to b minus a times the norm of f prime of psi, and you are done. Okay, so I think I went a bit over time. So yes, these are all the exercises I want to solve for today. So next time we're gonna be going back to notes. Okay, we're gonna go further into differentiability, just so we have enough tools to do even more exercises. Okay, and practice more with differentiability. So thank you for watching today, and see you next time. Okay.